Hello folks, welcome back. So in the previous unit associated with chapter 23, we essentially saw that we could conceptualize and understand concepts associated with electrostatic potential energy and electrostatic potential. We understood also that electrostatic potential has units of energy divided by charge, and we gave it a convenient name of voltage, and therefore we understood how to solve problems associated with charges moving through voltage differences and how much energy is acquired by those charges. So with that small understanding that we developed in the last section or last unit, let's go ahead and extend our understanding. And this time, what we want to do is improve in this unit our computational or calculational abilities. So we want to essentially understand the voltage difference associated with a point A out here, as shown in this figure, and a point B out here. And so what do? If we have a path that connects the point A to the point B, we essentially split that path into little segments. And associated with each of those segments, we calculate a displacement vector dr vector. At each of those locations, we indeed do have the electric field. And so we take E vector dot dr vector, take negative of that, and integrate it from Ra to Rb, which is what is shown out here. This will give us the potential difference between Vb and Va. The potential at point B, which is denoted as Vb, minus the potential at point A, which is denoted as Va. So with this, we know how to evaluate that potential. We know how to evaluate that electric field, and therefore we know how to evaluate the dot products, and we therefore know how to go ahead and do that line integral, at least in principle. However, in practice, it might turn out that line integral is a little too complicated for arbitrary paths. And so what I'm going to do essentially out here is that in this transparency, I'm going to essentially show you all that the line integral can be simplified in the case where all the displacements are in the radial direction itself. So instead of focusing on the figure to the right, we're essentially going to focus on the figure that is in the bottom. For the bottom figure, the situation is much simpler. So we see that the electric field itself is radially oriented for this positive charge, and so we can write the electric field E vector at any location as being equal to K times Q divided by the radial distance r squared times r hat. And we can actually write the displacement vector dr vector as being equal to some displacement dr times r hat. And therefore, the dot product of these two is very easy to take because r hat is essentially a unit vector and r hat dot r hat is equal to 1. And so if we take the dot product between E vector and dr vector, we essentially see that it is just equal to this guy. And so this integral is easy to do because K and Q are constants, and we just have an integral of the form dr over r squared, or dx over x squared if you think about it by using your calculus 1 or calculus 2 skills. And therefore, we can go ahead and do this integral and come up with this result. Now, one important convention to follow is that the potential at infinity associated with any charge is exactly equal to 0. And that's a very desirable convention to follow. And so with that convention in place, we can essentially go ahead and say that the potential associated with a charge at a distance r from that charge is just given by this very simple formula. This formula is practically as important as Coulomb's law, and so I would urge you all to essentially memorize it. And the other customary convention is that we want to choose to have the potential be zero at r is equal to infinity. Now with this, let me go ahead and demonstrate a point that I'd made in the last transparency, which is that even if we have an arbitrary path, let's say going from this point here to this point here, let me draw that path again. It came out a little badly. So let me go ahead and say that even if we have a path going from this point here to a point out here, that's not is necessarily not a radial path. We can essentially decompose that path into sets of paths for which we can realize that only the radial part matters. So we can essentially decompose the path from here to here as a path that is given by a path along this arc of a circle and a path that is exclusively in the radial direction. Now realize that the electric field associated with this point charge is in the radial direction, and therefore the line integral along this arc of a circle, that's the arc that I'm making solid right now, is zero. And so the only thing that contributes, if I might show it in blue, is the line integral in this radial direction. Likewise, as we focus on this arc out here, we can decompose that arc into an arc in an arc of a circle, which is the arc that I'm making solid right now, and a further path length that is in the radial direction. And we see again that because the electric field is radially oriented, its contribution along the circular arcs is essentially zero, and only the radial contributions are non-zero. So we realize that effectively we could have gone ahead and taken the line integral just from this radial location to this radial location, namely from this radial location out here to this radial location out here, and that is exactly what we did in the previous transparency. So we simplified our line integral so that we only focused on the radial part of the path that we were choosing. With this understanding and the convention that we have also established, we can now move forward. We can essentially say that the potential associated with any point charge only depends on the radial distance from the point charge and does not depend on anything else. And therefore we see that if we draw it multidimensionally, namely in the xy plane, then the potential associated with this point charge looks like this. This is the potential associated with a positive point charge, and so we can essentially draw it as follows. So this is the potential V as a function of r, and we can see that for a positive point charge, V as a function of r is just given by this function out here, where we say that V is equal to K times Q, where Q is positive, divided by r, and K is Coulomb's constant. If this charge were a negative point charge, then of course this thing would be flipped. So the vertical axis would be flipped, and we would actually have a situation where this would be a deepening potential. And if I were to draw it as a function of the radial direction for a negative point charge, then that potential would essentially look like this. Okay? So here, this would be V is equal to KQ over R, but in this case, Q is in fact negative for a negative point charge. So this gives us the potential associated with point charges, both positive and negative, and the figure above corresponds exclusively to the potential associated with a point positive charge. With that, let's go ahead and ask about the potential associated with a dipole. So here we see that at this location out here, we have a charge plus Q, and at this location out here, we have a charge minus Q. Therefore, we see that very close to the charge plus Q, the potential associated with the configuration of charges, equal and opposite charges that make up the dipole, is exclusively the potential associated with the positive charge. Likewise, if we so that's why we have this mountain peak happening out here very close to the charge plus q. If we focus very close to the charge minus q, we see that we have a very deep valley developing at the location of the negative charge, which is the valley that I just marked out for you. And if we try and now plot out the potential along a line out here, we can essentially say that let that line be the x-axis, for instance, and let this be the location of the positive charge, let this be the location of the negative charge. Then we have plus q out here, we have minus q out here, and if we plot out the potential along a straight line, we would essentially realize that as we move from positive infinity closer to the negative charge, the potential is going down. Here the potential is actually coming up again, and then it's going up towards the positive charge, and then it's kind of going down again like so out here. So we see that this is the potential drawing along one direction, along the x direction for a dipole, which is a pair of positive and negative charges. Close to the negative charge, we see that we have a valley of potential developing. Close to the positive charge, we see that we have a peak of potential developing. And that's not unusual because the function goes as kq over r, which means that close to the negative charge, it's the potential from the negative charge that dominates. Close to the positive charge, it's the potential from the positive charge that dominates. With this understanding, we can go ahead and move on and essentially assert our superposition principle. It basically says that the electric potential due to a configuration of point charges, namely several point charges, is just the sum of the potentials associated with each individual charge. So that's a very nice simple principle. And just like we had a superposition principle for the electric field, which was vectorial, this superposition principle is in fact much simpler because the electric potential is a scalar, and therefore we just have to do a scalar addition of the potentials associated with each of the individual charges in order to find the net potential. So we can therefore go ahead and answer this thought question, which says that the charges plus q, minus q, minus q, and plus q at the vertices of this square, and we're asked to find the potential at the center of the square. And please go ahead and see if you can find some sort of pointwise cancellation for the electric field, or what you can find for the value of the potential in order to find, or in order to decide which of these several options is indeed the correct option. So with this, we can now move forward, and we can now focus on the potential energy due to multiple charges being brought together. So imagine, if you like, that there is an initial charge q1 and the charge q2 is brought close to it out to a distance of r12. Of course, at infinity, these two charges, if these two charges are infinitely far apart, they have no influence on each other, and of course there is no potential at the location of one charge due to the other, and so the potential energy is zero. But as you bring the charge q2 in the vicinity of the charge q1, so imagine, if you like, that this charge q2 has been brought in from infinity and to this location out here, then it actually experiences a potential in the vicinity of charge q1. And that potential, that it actually develops a potential energy associated with being in the vicinity of charge q1. So I'm sorry, I shouldn't have said potential, but I should have said potential energy. And that potential energy, notice that at infinity, the potential due to charge q1 is just given by V infinity is equal to 0. At this location out here, at a distance of r12, the potential from charge q1 at r12 is essentially given by k times q1 divided by R12. And so we say that the change in potential energy, delta U, is actually equal to the charge Q2, which has traveled from a potential of V infinity to a potential of VR12. And so if we go ahead and fill in for this equation, we see that the change in potential energy is just given by K times Q1 times Q2 divided by R12. Okay? So if we bring two charges which are infinitely far apart and we bring them together, we are essentially developing a certain amount of potential energy associated with that configuration of charges that is given by K times Q1 times Q2 divided by R12, where R12 is the distance between those two charges. Now notice some important aspects associated with this formula. First of all, I might point out that this formula is extremely important and you should make it a point to memorize it. But now notice some important aspects associated with this situation. If Q1 and Q2 have the same sign, then the value of U, the potential energy associated with this system, is positive, and therefore it basically means that we have to do work in order to bring the two charges together. This is only natural because the two charges basically have a repulsive force between them, and so if you want to bring them together, you have to essentially do work to basically squeeze them so that they might want to come together. On the other hand, if the two charges have opposite signs, then you see that the potential energy associated with the system is in fact negative. What does that mean? It basically means that if you want to bring those two charges together, if you release them from infinity, those two charges will naturally want to attract towards each other and come together, and essentially you have to do work in order to keep them apart. In other words, the amount of potential energy is negative and work is done to keep the charges apart. Okay, so that's the important idea associated with potential energy associated with two similar charges and two opposite charges. I would also point out one more fact associated with this formula, which is that the potential energy is not associated with any one charge or any of the other charges, but is rather the potential energy associated with bringing these charges into the configuration in which they have been brought. In other words, if you think about an analogy, you could say that what is the potential energy associated with the Earth-Moon system? We know that the Earth-Moon system is bound together by gravitational potential energy, and they're basically locked so that the moon will never fly away from the Earth unless something unusual, gigantically unusual happens. But we therefore realize that the potential energy associated with the Earth-Moon system neither belongs exclusively to the Earth, nor does it belong exclusively to the Moon. This potential energy is just the energy of the configuration in which the Earth and the Moon find themselves together. So that's an important point to be made. And with this important point in place, we can essentially go ahead and ask what is the potential energy associated with a configuration of three charges, for instance, and that is actually shown to you out here. Now, I would rather go ahead and derive this idea for you all, which is essentially what we're going to do in the next couple of transparencies. So imagine, if you like, that we initially had a charge Q1 and no other charges around it. Then the potential energy associated with having Q1 and just Q1 sitting all by itself is essentially zero. Now, if you imagine that we take a charge Q2 which resides at infinity and somehow manage to bring it close to this location so that the charge Q2 is at a distance of R12 relative to the charge Q1, then we would essentially have an amount of potential energy associated with this two-charge configuration that is given by this U2 out here. Now notice that U2 is the energy of this charge configuration. Namely, it is not the energy associated with any one charge, nor the energy associated with with the other charge, but rather it is the energy associated with bringing these two charges in juxtaposition with each other. Now, imagine, if you like, that I want to bring a third charge from infinity to this location out here. Okay, so I want to bring a third charge so that its distance from Q2 is given by R23, and its distance from Q1 is given by R13. In other words, I'm going to go ahead and take the charge Q3, bring it from infinity all the way to this location out here. And so this is the charge Q3 at the location to which we have brought it. We have to then ask how much energy has been expended to bring this charge to its current location. The answer is that first we have to go ahead and find the electrostatic potential at that location. And so let's focus on the lower figure now. The electrostatic potential at this location, due to the original two charges Q1 and Q2, is essentially given by V is equal to K times Q1 divided by the distance from Q1 to this position 3, which is given by R13. Plus, because of the superposition principle, I have to add in the potential at this same location due to charge Q2, which is given by K times Q2 divided by the distance at the position 3, the distance between position 3 and position 2, namely R23. And so we can essentially say that the total energy expended in bringing this charge Q3 from infinity to its current location is just given by multiplying this potential with the charge Q3. So we multiplied this potential out here with the charge Q3, and this is the amount of potential energy that we have expended, or we have built up, in order to bring the charge Q3 from infinity to this position where it is in the vicinity of charges Q1 and Q2. So this is the additional energy, in addition, of course, to the prior energy that we expended to bring charges Q1 and Q2 into configuration with each other. This energy down below is the additional energy that we have to expend in order to bring Q3 to its current location. With this understanding, we write the total electrostatic potential energy of the system by this line given out here. So this is just the addition of the two contributions that we saw in the previous transparency. Now let's go ahead and write out this expression and break it up into a certain subset of expressions, and we will actually derive a very nice insight from this procedure. So let me go ahead and show you that procedure. So I take the first term in the sum out here, that's this red term, and I write it as a sum of half of this term out here and half of this term out here. Okay? I'll choose a different color, maybe a blue color, and I'll underline the second term out here. This term can be written as a sum of this term down, half of this term out down below, and half of this term down below. So we have a third term in the above equation. So let's go ahead and underline it and show it with a green color. So we essentially have this term, which I've shown with green, and I can write it as half of this term plus this term. Now let's go ahead and see what happens when we combine all these terms in a particularly insightful fashion. Notice first off that the half associated with my taking each of these terms, each of these three terms, and splitting them into six terms, that factor of half that I was mentioning is actually still captured in this equation out here. Now let's go ahead and take the first pair of terms and combine them together by factorizing out Q1. Notice that if we factorize out Q1, then what we have left behind in the bracket is in fact the potential at the location of Q1 from charges Q2 and Q3. Namely, it is equal to KQ2 over R12 plus KQ3 over R13. Let's now focus on the second pair of terms that we have. And we realize that it can be factorized so that we take Q2 out of these two terms, and therefore the thing then inside the brackets can be written as KQ3 over R23 plus KQ2 over R12. In other words, it is the potential at the location of charge Q2 due to the charges Q1 and Q3. Now let's go ahead and factorize from the last pair of terms that we have out here, and it can be written as Q3 times whatever is in the brackets, and what we have in the brackets is KQ1 over R13 plus KQ2 over R23. What is the term in the brackets? The term in the third brackets is basically the potential at the location of charge Q3 due to charges Q1 and Q2. So we see that we can write this as half times each charge times the potential at the location of that charge due to the other charges that make up the system. So the word other is very important, and this factor of half is very important because most students somehow eventually confuse this factor of a half and forget about it or don't use it, resulting in a wrong solution. So with this understanding, we're now in a position to write out the electrostatic potential energy of a configuration of n point charges, and it is actually given by half of each of the charges Qi, half of the sum of the products of each of the charges Qi and the voltage associated with that charge, the voltage at the location of that charge due to the other charges that make up that configuration of charges. This gives us in a sense the measure of the work needed to bring together that configuration of charges from a situation where they have infinite separations relative to each other. So this actually is a very useful and important formula, and we will essentially go ahead and understand how this formula worked in the next problem. So this next problem shows us four charges assembled at the vertices of a square, and it essentially asks us to first sequentially assemble this charge configuration, and secondly show that if we use the formula from the previous page we get the same answer. So let's go ahead and first zip through the first part of this problem. So imagine, if you like, that only the charge at the location A is present, then the work required to put that charge at its current location is exactly 0. Now imagine that the charge B is pulled in from infinity and dragged to its current location. The charges C and D are still not present. In that case, the work required to bring in charge Q to the location B is just given by the potential at the location B due to charge A times the charge that is located at point B, and that's equal to KQ squared divided by A, where A is the length of the sides of the square. Now we can ask that now we can say that the charges at the locations A and B are present, and we want to bring in from infinity a charge Q, which we will then park at the location C. In that case, we have to essentially say, what is the potential at C due to the original two charges A and B? We can find that potential by saying that V sub C is essentially equal to KQ divided by A, which is the potential at C due to the charge at B. But now notice that the charge at A is located along a diagonal, and so we have to include the length of the diagonal, which is just square root 2 times A. And so we essentially say that we have to add in KQ divided by square root 2 times A. So this gives us the potential at location C due to the charges at the locations A and B, and that has to be multiplied by the charge that is now parked at C in order to get the additional work required to put charge Q at the location C. Now we can then ask, what is the potential at the location D associated with the charges A, B, and C? Notice that as yet in the narrative, we have not pulled in the charge from infinity and parked it at the location D. That potential at the location D due to the charges at the locations A, B, and C is given by KQ over A from the charge at location A, KQ over A from the charge at location C, and KQ over square root 2A from the charge at the location B. And so we have a comprehensive potential at the location D due to the charges A, B, and C. Now if we pull in a charge Q and take it from infinity to the location D, then that potential energy is given by the multiplication of the bracket that we just evaluated times the charge Q itself. And this gives us the additional work required to pull charge Q from infinity to a point D. And then we can go ahead and add in WA, WB, WC, and WD. And that's exactly what is done out here. And we get this final energy to, or then we find the total work required to assemble the four charges, which is basically the potential energy associated with this configuration of four charges. So we see now that from a very laborious process, we have taken one charge after the other and assembled it in order to form the charge configuration out here. And at each point, we have kept track or kept a tally of the amount of energy that we're expending or utilizing in order to assemble this configuration of charges. But my purpose out here is to actually go ahead and show you that calculation can be done much simpler if we go ahead and use this formula that we have developed out here. And this formula is actually the good formula to use because it keeps you on track. So with that in mind, let's go ahead and just realize that from the symmetry of the situation, the potential at any one point due to the other charges that make up this configuration of charges is easy to evaluate. So let's take the point C and realize that the potential at C due to charges A, B, and C is given by KQ over A from the charge at the location B plus KQ over A from the charge at the location D plus kq over square root 2 times A from the charge at the location A. In other words, the charge at the location A is diagonally across from the position C and therefore is given by kq divided by that diagonal distance. So once we've done this, we realize that the potential at D essentially evaluates to the same number because of symmetry considerations. Likewise, we see that the potential at location A evaluates to the same number. Likewise, we see that the potential at B evaluates to the same number. So we can actually go ahead and say that the total energy associated with this charge configuration is just given by half. That's the half that we have in our formula, times the product of each charge with the potential at its location due to the other charges that make up the charge. And we have a factor of 4 simply because we have 4 of these charges to be considered. That's the 4 charges in the summation that we're considering. And that tells you that this formula out here becomes a very simple formula to evaluate because we just realized that this factor of 2 and this factor of 4 causes a factor of 2 to be present out here. So we have just to take whatever is inside the round brackets and multiply it by 2q. So if we do that, we essentially get 2q times 2 times kq over a, which gives rise to this part out here, and 2q times kq over square root 2a, which gives rise to this part out here. And the summation of these two parts gives us the potential energy, the electrostatic potential energy associated with this configuration of charges. Notice that I will again go ahead and reinforce that the potential energy is associated with the entire configuration of the charges. No one charge owns the potential energy associated with this configuration. With this, we can essentially go ahead and solve somewhat more complicated problems like the one shown out here, and I would essentially urge you all to do it on your own time, or perhaps we can do it in class. Now let's go ahead and identify the fact that this concept of having this factor of half is not just a computational accident, but rather is very fundamental. To do that, I would like to essentially show you that this factor of a half shows up even in other types of calculations. So imagine, if you like, that we have now a shell of charge. And we know from our study of Gauss's law that everywhere exterior to the shell, the electric field associated with this shell of charge, which has an amount of charge Q, is essentially just given by K Q divided by R squared. So essentially the shell of charge behaves almost as if that entire charge is concentrated at the center, as long as we agree to look outside the shell of charge. So with this, it is not difficult to understand, therefore, that the electric potential at any location associated with the shell of charge is just given by kq divided by r, as long as we are located outside of the shell of charge itself. Therefore, if we take this expression for the potential associated with the shell of charge at any distance r that is greater than the radius of the charge itself, and we ask what is the potential at smack dab on the boundary of the charge, we come up with this formula out here. Now, imagine that we want to go ahead and build up the charge on this sphere. We want Q to go all the way from Q is equal to 0 to Q is equal to big Q. Okay? Then we can do it by essentially taking infinitesimal pieces of charge, dq, from infinity and bringing them close to the surface of this shell of charge and basically sticking them to the charge itself. In other words, the shell initially has a charge q, and we bring in an infinitesimal amount of charge so that after we brought this infinitesimal amount of charge in, we have a charge of q plus dq on the shell. How much work do we do, or how much electrostatic potential energy do we gain? The answer is that is given by the increase in electrostatic potential energy dq, which is just given by the potential at the surface of this shell, and that expression we know. So we take the potential associated with the surface of the shell times the amount of charge dq that we have moved in from infinity. And once we multiply those together, we get the infinitesimal associated with increasing the charge on the surface of the shell from an initial value of q to a final value of q plus dq. So we've obtained the infinitesimal increase in the potential energy via this expression out here. What we're going to do next is essentially integrate so that we can go from q is equal to 0 to q is equal to capital Q. So we have du as being equal to the potential on the surface of the charge times dq, and we can express v as being equal to k times q divided by the radius of the shell, which is big R, times dq. And this is the infinitesimal amount of potential energy associated with increasing the charge on the surface of the shell from q to a value of q plus dq. And we can now go ahead and say that the total potential energy is just equal to an integration of k q over r times dq, where this integration goes from q is equal to 0 initially to q is equal to big Q in the final configuration. So now notice that k and r slip out of the integral, so we can write this as k q, I'm sorry, not kq, I'll take that back. So we can write this as k over r. That has slipped out of the integration because k is a constant, the radius of the shell is a constant, so big R is a constant. And now we're going from 0 to big Q of q times dq. This integration is simply of the form x times dx, and its integration is x squared over 2. So we can essentially write this answer as being equal to half of k times q squared over 2. Q squared over big R, I'm sorry. Now let's go ahead and factorize this. So we can write this as half times q, and what is left behind is just kq over big R. But what is kq over big R? That's actually the potential on the surface of the shell in the final configuration where its charge has been increased to a value of big Q. And so we can write this as being equal to half of Q times the potential on the surface of this charge. So this tells us that this factor of half that we find in our final formula is not an accident. It occurs for point charges and it occurs for continua of charges. And we will actually see in the next chapter that this factor of a half comes up even when we ask for the energy associated with capacitors and so on and so forth. So we now have a good understanding of where this formula comes from and why this factor of a half is essential. With this, we have rounded out or finished up this subsection, and now let's move on to the next subsection. So we're left with a very interesting situation. We know that if the electric field for a point charge or a configuration of point charges is given, then we can essentially find the electric potential for that configuration of point charges. We can do that by a process of integration. So we see that the electric potential for a system of point charges is a scalar value. In other words, it's a scalar field. At each location, there's just a number associated with that electric potential. On the other hand, the electric field associated with that configuration of charges is a vector field. In other words, associated with a configuration of charges, at each location, you have an electric field vector. So this makes us realize that if we can obtain the potential at any point in space by carrying out an integration of the electric field, then can there not be a way of reversing that procedure? In other words, given an electric field, we can always find the electric potential associated with that electric field, but can we not obtain the reverse of that? In other words, given an electric potential, which is a scalar field for a configuration of charges, can we not therefore back up and find the corresponding electric field itself, which is a vector field? It turns out that indeed we can do such a procedure. Let's go ahead and focus on the next transparency. In the next transparency, we're seeing in this figure on the right that we have a certain number of electric field lines, which is shown to you out here. Imagine, if you like, that we make a displacement, which is dl vector, going from some initial position to an infinitesimally small position that is nearby to it along the x-axis. We know the potential at the beginning of this displacement. We know the potential at the end of this displacement, and therefore we can evaluate the infinitesimal change in the potential. And we know from our formula that the infinitesimal change in potential is always equal to minus of E vector dot dl vector, where dl vector is the vector that takes us from this initial location to this final location out here. So we can go ahead and say that since our dl vector was chosen to be along the x-axis itself, we have minus E vector dot dx times I hat, and therefore if any vector is dotted with I hat, that basically leaves us with the x component of that vector itself, where I hat is the unit vector in the x direction. So we get our final result, which is that the change in potential going from the initial location to the final location, which we denote as dv, is equal to minus of ex times dx, simply because we have taken our displacement to be along the x direction. Now go ahead and realize that we can take this dx and bring it over to the other side in the denominator. So we obtain ex is equal to minus dv by dx. And we can actually prettify this formula that we've obtained by realizing that we could make a displacement in the x direction or in the y direction or in the z direction. And so here we've specifically made a displacement only in the x direction. So we should take, in fact, dv by dx. We can correspondingly make displacements in the y direction and in the z direction, and therefore we can obtain the electric field in the y direction as being minus dv by dy, where of course the dv by dx and the dv by dy are to be taken as partials. And we can obtain the electric field in the z direction by taking an infinitesimal displacement in the z direction and asking what the potential change is in the z direction, and therefore obtain Ez, which is just given by minus dV by dz. This actually tells you that if the potential is specified as a function of x, y, z, then we can actually obtain all components of the electric field vector, because it is the x component of the electric field vector is just given by minus dV by dx. The y component of the electric field vector is just given by minus dV by dy. And the z component of the electric field vector is just given by minus dV by dz. This tells you that we have a simple and obvious formula for obtaining the electric field at any given location if we are indeed given the electric potential at all locations. So given an electric potential, we can back out or extract an electric field vector associated with that electrostatic configuration. So now let's go ahead and see some examples. We have studied in chapter 22 that the electric field associated with an infinite sheet of charge with a positive surface charge density sigma is given by the electric field that is shown by these orange arrows out here. Notice therefore that the electric field Ex is a constant. What does that tell you about the electric potential? The electric field Ex must be equal to minus dV by dx, which basically tells you, first off, that the surfaces of constant potential have to be these vertical lines or vertical planes shown out here. If you extend it in 3 dimensions, it would be a vertical plane. And furthermore, it tells you that dV by dx, namely the gradient, the change in the electric potential, is constant for each constant distance in the x direction. So, for example, if the electric potential out here is 0, then the electric potential out here could be minus 10, the electric potential out here could be minus 20, the electric potential out here could be minus 30, and we realize that we have constant amounts of decrease in electric potential associated with constant displacements in the positive x direction. It need not be minus 10, minus 20, minus 30. It could also be minus 5, minus 10, minus 15. It could also be minus 20, minus 40, minus 60. But what I'm trying to convey to you is that you have constant amounts of decrement in the electric potential as you move constant amounts of displacement in the positive x direction in this figure. So this actually gives you the correct insight associated with the equipotential surfaces associated with the electric field that is produced by a sheet of charge. Okay? And because the field is uniform, the equipotential surfaces are also uniformly spaced, one with respect to the other. So that's the essential insight associated with this problem that we have seen out here. Now, the question is, what is the relationship between the electric field and the electric potential for a point charge? The answer is that the equipotential surfaces associated with a point charge are in fact spherical, and therefore the electric field ought to be radial. So that is axiomatic, because basically we saw in the previous unit that the electric field is perpendicular to the equipotential surfaces. And we also understand another important insight, that notice that the electric equipotential surfaces closer into the charge are closer spaced. The electric equipotential surfaces farther out are farther apart, which basically tells you that the electric field closer to the charge is stronger. The electric field farther from this point charge is weaker. And that's all consistent with Coulomb's law as we have studied before, but we're getting another way of reinforcing these very same ideas out here. Now we can essentially ask for the electric field and electric potential associated with a dipole, and we've already studied that. So we see that we have a peak at the location of the positive charge. So the positive charge is located out here, and we have a peak developing out here, and the negative charge is located out here, and we have a valley developing around the negative charge. Notice that close to the positive charge, you have equipotential surfaces that are almost very close to the positive charge. You have equipotential surfaces out here that are almost circular. Very close to the negative charge, you again have equipotential surfaces that are almost circular. Why? Because these equipotential surfaces are responding to the more dominant source of potential, which is the charge that they're closest to. Farther away from the positive charge or farther away from the negative charge, the electric equipotential surfaces cease to be circular and in fact have an ovoid type shape. Okay, so with these insights, we're now ready to go ahead and do our next thought question. In this thought question, we're told that we are given the potential as a function of distance, which is in this plot in the left panel is shown as R. So focus on the left panel. This is a plot of the potential as a function of distance. We notice two things. We notice that it's a straight line, which means that dV by dr is a constant. Furthermore, we realize that it's a straight line that is sloping downwards. In other words, it's a straight line with a negative slope, and therefore dV by dr is in fact negative. What does that mean for the electric field? Recall that the electric field is not given by dV by dr, but rather it's given by minus dV by dr, and therefore we realize that the electric field in the r direction is just given by a positive constant number. In other words, I'm sorry, dV by dr per se is a negative constant number because this is a straight line. However, minus dV by dr is a positive constant number, and so we realize that the electric field is a constant with respect to r, and it's a positive constant with respect to r, which is why D, namely the line number 4 that is shown in the panel on the right, is in fact the correct answer to this problem. So with this thought question demonstrated in front of you, we're now ready to move on to this next thought question, which we'll pick up on in class, but it actually it's a very nice thought question because it shows you the electric potentials associated with various configurations that we have studied, and therefore it asks you to essentially identify so this problem essentially asks you to identify which plot of electric potential corresponds to which configuration that is mentioned on the top. So with this, I will essentially thank you for paying attention, and I will look forward to seeing you in the next unit. Thank you and see you later. Bye-bye.